To start things off today, we're going to be talking about displacement. Displacement. Displacement is often used kind of interchangeably with distance, but it's not quite the same thing. And I guess the easiest way to get started is to talk about a coordinate grid a little bit. So here's a coordinate grid, and let's say we start out at x equals 0. Now, if we are at x equals 3, then the distance from the origin is 3 units. If we start there and we go over to x equals 7, then the distance from the origin there is 7 units. That's not the displacement. Displacement is defined as delta x. Delta means change in. So xf minus xi. Now what does fx and xi mean? Fx means final position, and xi means initial position. Subscript f and subscript I will mean final and initial for pretty much the entire year. So that's something you need to get through your head. So for our example over here, we wanted to find the displacement. We could just plug in. We could say, okay, the displacement in the x direction, delta x. The final position was at 7 units. The initial position was at 3 units, so 7 minus 3. The displacement was 4. In most cases, displacement is the same as distance traveled, but not always. For instance, we could have started here, moved to way over here, and then come all the way back to right here, and our displacement would only be that much. So in the end, our displacement would be, we started at 2 and went to 1, so in this case it would be, we started at 2, oh excuse me, we did it wrong. Final minus initial. Final was 1, initial was 2, so our displacement would be -1. We can have negative displacement. Generally we'll define to the right as positive, to the left as negative. Also, when we get into 2 dimensions, up is positive, down is negative. You know, just to be consistent. It's generally how we do things. So backwards is generally negative, forwards is positive, up is generally positive, down is negative. So that's what we mean when we're talking about displacement. Alright, so having talked about displacement, we're now ready to talk a little bit about velocity. Velocity, and we'll just give it to you, average velocity, which we'll put as v bar. This means average velocity. Sometimes you'll just see v sub avg. Either way, I'm going to use v bar just because it's easier to write. Average velocity is defined as the change in displacement in a direction divided by the change in time. Okay, changes, as we are used to, is equal to the final position minus the initial position divided by the final time minus the initial time. Now, we are rarely going to be dealing with initial and final time. Most of the time we'll just be told something happens over 4 seconds. Okay, delta t is really just a time interval. how much time passed. And usually that's going to be given to us. Like, very occasionally, we'll have to figure it out. Like, maybe we'll say the clock says 30 seconds when something happens, and then by the time the next thing happens, the clock said 57 seconds. Okay, we'd have to find the interval, which obviously is 27 seconds. So that would be our, since this would be our initial time, this would be our final time. We get subtracting at 27. Let's not get too hung up on that. That's easy stuff. So, move all that out of the way. So, this is our definition of velocity. Now, notice that if our initial position is larger than our final position, we could end up with a negative velocity. Well, what do you think that means? Well, negative velocity would mean you're going backwards. So that's not a big deal. Okay, for example, let's imagine that you traveled 370 kilometers in 5 hours. Alright, and we wanted to know the average velocity. Well, 370 is our displacement, so that's our delta x. 5 hours is our delta t, so we just plug right in. So v equals delta x over delta t. Plugging in, we get 370 kilometers divided by 5 hours. Dividing that, we would end up with 74 kilometers per hour. That's pretty simple. Now, please be aware that I could give you instead, I could maybe give you velocity. Maybe average velocity is 10 meters per second. I could give you time, or the time interval, maybe 45 seconds, and I could ask you for the displacement. How would you do it? The same way. You would just plug in. This time we're looking for delta x, so you'd have to solve for delta x, and that shouldn't be hard. Everyone should be able to do that. Alright? A couple more quick things about velocity. Remember, our formula is v equals delta x over delta t. Now, if you remember, v is velocity, x is distance basically, and t is time. This is really the same formula as this one that probably looks pretty familiar. D equals RT. Distance equals rate times time. You know, we'll say, well, that doesn't look the same. Well, watch. If we take this, put it over 1, and cross multiply, we get delta x equals v times delta t. Well, delta x is really just distance. V is really just the rate. And then t, of course, is time. So if all else fails on velocity problems, you've probably seen distance equals rate times time before. So just use that. I'm not telling you that's preferable, because it's better to keep the notation consistent with what we're going to be using throughout the year. But in a pinch, don't forget that you already knew this. You know that distance equals velocity times time, or rate times time. Now, velocity is not quite the same as speed, because velocity, and here's the important distinction, velocity has direction. And magnitude. Velocity has direction and magnitude, meaning direction is where, and magnitude is how much. Oh man. Okay, so velocity is really going to be like 25 meters per second north, or 25 meters per second east, or whatnot. Speed has only magnitude. Okay, so speed is only how much quantity. So it'll just be like 10 meters per second. Doesn't have a direction. And that's a subtle thing that could come up on a quiz or a test. I could show you some numbers and ask you which one's a velocity. A velocity needs a direction. So sometimes the direction can be as subtle as negative 14 meters per second. That tells you it's in the opposite direction, in the negative direction. So be careful. Okay, so earlier we played around on Yinka a little bit. And so here I'm going to put my little yellow car. And we're going to do displacement in the x direction here. And we can give it a certain amount of time, or we can actually even give it a velocity. We can also have it graph displacement. And we can see how the displacement when there's no velocity is a straight line, because the displacement is 0. We haven't moved. Now, if I give the car a velocity, we see that it's a straight line, and then it goes back to being flat. So while it was moving in a fairly high speed, we saw the displacement increase over time. And now we're at rest again, and so we've gone back there. Go back the other way. Whee. Okay. So we can, watch and see what different things happen here. What if I give it a very small velocity? We can watch it go. Okay. What if I give it an even smaller velocity? Okay, and now let's give it a really big one. As big as I can. Let's give it a really big one now. Like that. So that's almost a vertical line. So hopefully, by playing around with this a little bit earlier, you saw that there was a relationship between the slope of the line depending on the displacement. If we increase the displacement like this, we get a certain, very flat slanted line. This is going very slow. But when we go faster, we get a more steep line. So, and if we stop, then our line flattens out. So since this is a distance time or displacement time graph, you should be able to look at a graph and be told it's displacement time and figure out what's going on. Flat lines mean you're not moving. Slanted lines mean you are moving. And if we start backing up, we have a line slanted down. If we start going back forward again, we're going to have a line slanted up. So that's interesting, and that's something that you are going to be expected to know. Now the interesting thing about that is that if we do have a coordinate grid, and we've got a straight line for a distance time graph, think about the slope of this line. What is slope? Slope is rise over run. So what is the rise of this? The rise of this would be d. And, well, here, back up. Slope is the change in x, excuse me, wrong. The change in y over the change in x, right? Well, the change in x is going to be the change in time, right? Because time is in the x direction. The change in y is going to be the change in distance, or in this case, yeah, distance. Well, distance over time. Average velocity equals, our previous one said the change in x over the change in t. Now I don't want you to get confused here, but in this case our distance is the change in x, even though the x direction in here is time. That's why I say I don't want you to get confused. But the point I'm trying to make is the slope here is the velocity. If you have a constant slope, if you have a straight line, that straight line is your velocity on a distance time graph. So that's sort of interesting. Now, unfortunately, you won't always have a constant velocity. You may have a situation where you've got your grid and your distance time graph looks like this. It's a curve of some sort. Now here we can't take a slope of a curve, but if we wanted to know the velocity at a particular moment, like if we wanted to know the velocity right here, what we need to do is find the slope of the tangent line. And if you remember from geometry, a tangent, and I can't draw it very well on this, a tangent is a line that touches a curve at a single point. So if we wanted to know, and I'll put a different color, if we wanted to know the velocity at that point, we would need to draw a line tangent to that curve and find the slope of that line. And that would be the velocity at that point. That's called instantaneous velocity. And I'm not going to be asking you to do that anytime real soon. But that's something just to remember. If I ask you about instantaneous velocity, that means this velocity you're going right at that second, right at that instant. Up until now, we've been talking about average velocity, so like over an interval. So that's about all I have for velocity. You'll have several problems. Make sure to get help if you're confused, if you're stuck. Hopefully no one will be. This should be pretty straightforward. You'll have a few graphs to look at and a few problems to work finding either velocity or displacement or time. And it's a simple little formula. So everybody should be able to do that without much trouble. Let's also go ahead and talk about acceleration today. Acceleration is, at its most basic, a change in velocity. So whereas velocity was a change in displacement, acceleration is a change in velocity. And we're going to have average acceleration, which will literally be delta v over delta t. Once we know that delta in physics means Vf minus Vi over Tf minus Ti. So imagine I told you that a car started at rest, so that would be my Vi, 0 meters per second, and then at the end, Vf, maybe it was going 30 meters per second, and maybe it took 4 seconds to do that. And we wanted to know the average acceleration. So what we have is looking for average acceleration. We know Vf, 30 meters per second. We know Vi, 0 meters per second. And we know the time, which was 4 seconds. So simplifying this, 30 minus 0 is 30. So we have 30 meters per second divided by 4 seconds. 30 divided by 4, that's 15 over 2, so that's 7.5 meters per second divided by seconds. Well, that's going to be meters per second squared. And meters per second squared is our basic unit of acceleration. So whenever you have acceleration, it's supposed to be in meters per second squared. You'll have a few problems on acceleration in today's work as well. So we played a little bit with Yanka earlier with dealing with acceleration also. If we have a velocity by time graph, a straight line represents a constant acceleration. We'll pretend that's an n. Okay. And because it's a constant increase of velocity. And this slope, m here, see it would be m would be delta v over delta t, which is average acceleration. So the slope of a velocity time graph is acceleration, just like the slope of a distance time graph is velocity. So that's interesting. Also, much like our other graph, if we had a situation where the graph was some kind of curve and we wanted a particular instant of velocity, or acceleration, excuse me, we would need to do a tangent line, just like we were doing earlier. And some of you may learn about this in calculus a little bit. So, if we wanted an instantaneous acceleration, of something with a non-constant acceleration, is something where it changes with a curve, we would need to find the point we wanted the instantaneous acceleration at and draw a tangent and find that slope. Again, probably not going to be asked to do that anytime real soon. Just something you really ought to be aware of.